approach infinity in the sense that they can grow without bounds, but they can never be equal to infinity. This has to be kept in mind, okay? In no calculation shall we ever consider n to be infinity when n is a natural number. Infinity is not an element of n. Okay, so this is remark to 130. Next, remark to 140. This remark is even more important. Yes. So the way we have introduced the natural numbers, that introduction is axiomatic rather than constructive. We will now try to understand the meanings of these words. Axiomatic rather than constructive. Axiomatic, of course, simply because we have introduced them using axioms, and we have just simply said that there is a number system that satisfies those axioms or those properties. Constructive is something different. In constructive definition or constructive treatment of something, we will actually construct it, the components of what we are defining, from something more primitive. Okay. For example, if you consider it, see, before defining natural numbers using the Peano axioms, we said that there is another way of defining them using cardinalities of finite sets. Cardinalities of finite sets. Okay, this is a constructive definition because it is using sets to define natural numbers, not some abstract property. No, it is defining the natural numbers in terms of something that is already known. Although we don't know sets yet formally, but still when we will do this, then this will be a constructive definition. Now, so what is the difference between these two sort of treatments, axiomatic versus constructive? In axiomatic, what we do, we are not concerned about what natural numbers are. What natural numbers are, we are not concerned about that question or about that aspect of natural numbers. That is, for us, natural numbers are some abstract concepts which satisfy certain given rules or axioms. Here, however, if we define natural numbers using cardinalities, natural numbers can be shown to be sets. Okay. Now, when we do mathematics, it's not really necessary to know what the objects are. So, for example, in the axiomatic treatment, we won't discuss what natural numbers are. We haven't said anything. We just said there exists a system which satisfies those 5 axioms. That's it. That's enough for us. In particular, we have not said what the natural numbers are in the sense what they are made of, whether they have some connection to some physical objects. You see, according to this treatment of natural numbers, this is the one we come across in our childhood. 3 bananas, 2 apples. From these sets, we learn to recognize 3 to these numbers. Okay. So, according to this definition, the numbers are coming from a physical situation which arises in the actual world. However, in the advanced treatment, numbers are not necessarily associated to something physical. They are abstractly treated as some entities on their own which satisfy some properties. So, according to our definition, it does not matter whether this number 3 is actually 3 bits in an abacus or 3 bits of a computer memory. There is no difference. We are concerned only about the concept 3, not what it does or what it measures, etc. So that is a somewhat deeper philosophical aspect of these two definitions, which shows their distinction. And as far as mathematics is concerned, this distinction of what the numbers are, it does not matter actually. It is of a more philosophical nature to think what numbers actually are. In fact, this takes us to one of the very first videos that we made, where I discussed the philosophy of mathematics, where I said something about the sense in which a mathematical object can be said to exist. There are two schools of mathematics with differing views on this. If you remember, one school is called the Platonists, who believe that the mathematical concepts exist outside of our brain and they will continue to exist even we don't exist. If we cease to exist, they will continue to exist. So for them, mathematics is a science. Whereas formalists are the ones who believe that mathematics is our creation, and that's why, since it's a creation, it's an art. But those two differing philosophical viewpoints don't actually affect the mathematics. See, then also when I introduced those viewpoints, I said that they will not affect the mathematics, and that's the case, because we are concerned about the abstract concept 3, not 3 bananas or 3 pens, for example. Okay, so there is no difference mathematically between those things. Now, to further this thing, there is one more remark. What this remark says, I can read it from here, since it's better to hear what Terence Tao has to say than to hear what I have to say, right? So he says, historically the realization that numbers could be treated axiomatically is very recent. Previously, people believed that numbers always had to be associated to something which comes up in real life. Okay. Later on, mathematicians came to know that this is not the case at all. They can be treated using only properties. And this view is not much more than 100 years old. Before then, numbers were generally understood to be inextricably connected to some external concepts, like these sets of some objects, right? Such as, counting the cardinality of a set, measuring the length of a line segment. That's how you can make sense of positive real numbers. Okay. or the mass of a physical object, etc. This worked reasonably well until one was forced to move from one number system to another. So for instance, if you think of these numbers 3 and 2, then they can be conceptualized very well using sets of objects. 3 something, okay, some 3 items or some 2 items. But if we try to conceptualize other numbers, say -2 or √3, or for example 3 plus 4i, then this counting that now they are not associated to counting sizes of sets or measuring sizes of sets in any way. Of course, you can try to think of this as the length of some line segments, say. But these are, as you go to higher and higher number systems, it becomes quite difficult to think of them as coming from something physical, some physical concept. That is because it's unnecessary. Numbers have a life of their own, and they are not necessarily connected to something physical. Okay, and this point is not understood by many people. That's why you see not just laymen but mathematicians themselves in the naming of these classes of numbers itself, you can see irrational numbers, irrational, as if it's not rational in the ordinary sense of the word. Complex, in the sense that it's too complicated to be understood, and this one is the worst. Imaginary, as if the numbers don't exist at all. These names have created more trouble for the numbers. It gives the wrong impression that somehow imaginary numbers don't exist, real numbers exist. These things are sheer nonsense. I have already discussed about this in mathematical philosophy. So when people had to move from one number system to another, these are some great mathematical advances, okay, but they led to a lot of unnecessary philosophical anguish and debate and war among the mathematicians as to whether -2, √3 and these are legitimate numbers. In fact, the Greeks did not believe that irrational numbers exist. They only believed that rational numbers exist. Nowadays, of course, we don't have such poems. So it's a great discovery of the 19th century that numbers and everything else in mathematics can be understood via axioms or some properties that the objects are supposed to satisfy. And this sort of associating numbers to something physical just for the sake of making the numbers look more real is entirely unnecessary. But you can make them you can associate them to something physical, but that is applications. Applications of these number systems to outside of mathematics, that is an entirely different thing. For example, you can use negative numbers to measure sub-zero temperatures, things like that. Okay. So now we have seen all the axioms and we have discussed some aspects of them in the form of these remarks. Now, one advantage of these axioms is that we can now define sequences recursively. Okay, so let's just